Hi, welcome to MathSpellBook, everyone. I'm your host, Peter, and basically we are going to get into continuing our Origin of Math series here on MathSpellBook. So if you're watching this on YouTube, don't forget to drop a comment, hit a like, and subscribe to the channel. If you're watching this on Twitch, welcome. You're catching us live for the continuation of the Origin of Math series here on MathSpellBook. So I will join up with our lecturer Sascha, and he will continue on where we left off last time, which was basically getting the values of the square root of 2 through a Cauchy sequence. And basically today I think we're going to finish up constructing the real numbers. So I will join up with him right now. Hey Sascha.
Hey.
We're on stream, so it's all yours.
Hi.
Alright, so what are we gonna do today?
Can't hear you. Hold up.
Okay. Let me see here. Let me check if it's on my end. There we go. There we go.
Hello?
Yep.
Oh yeah, now I hear you.
Okay, I think it's because of the Windows update. Like I had to check my settings just in case, because that sometimes happens.
Okay. So we were in our quest to build the real numbers.
Yep.
And last time we kind of did a detour where we showed that square root of 2 was not a rational number, but we could still approximate it by a Cauchy sequence.
Yeah.
And sort of the moral of this story was that the Cauchy sequence are kind of able to see those numbers that are not rational numbers.
So,
like we're able to build Cauchy sequence.
So I'll summarize what we learned last time. So in one sentence. So basically, like we learned that a Cauchy sequence that does not converge, basically there means there's like a lot more stuff to, I guess you can say, not the elements, but basically like a set that basically is within like, I guess the set you're studying in this case. If that makes any sense.
Yeah. So the Cauchy sequence were able to see irrational numbers. That was kind of the point. So they're kind of seeing like the missing part of the rational. And today we will build a real number. So maybe one strategy will be to say, okay, well, we could choose the real numbers to be the set of Cauchy sequence, right?
Okay.
That could be an idea. Maybe what about defining the real number as the set of Cauchy sequence? But then we run into a trouble because the thing on the right is kind of dumb because, for example, if we give it the sequence an is equal to 1, so is equal to 1 for every term, and give the sequence bn is equal to 1 for n greater or equal to 1 and 0 for n is equal to 1, or n is equal to 0, then as Cauchy sequence they're different.
Yeah.
Because for being equal as a Cauchy sequence, you have to have all the same all the same term, which is not the case here.
Okay.
But I mean, this is in our mind, the sequence an and bn should be represent the same rational number. Here, right. Namely 1, right? So what we're gonna do is we're gonna do some quotient out to make sure that those sequences are equivalent.
Okay.
So what we're gonna quotient out is by the following ideal. So we have to show that it's an ideal, and we're gonna do all this check today. So what is this guy? So I0.
So it's the Cauchy over the ideal 0, right?
Yeah. So the ideal with a little 0 on the underscript is just the set of all sequences that converge to 0.
Mm-hmm.
Okay. And if you look here, I'm a little example I gave you. Here you can clearly see that if I do an minus bn, then the difference will be inside of I0, right?
Yeah.
Clearly, if I subtract the two, they will go to 0 because they're equal at every term except for the first except for n is equal to 0. But sequence doesn't really care what happened at the start of the sequence. They only care about what is happening down the line, right?
And could you also remind us on what an ideal is? So those that haven't caught up.
So an ideal was just some set of a ring, some subset of a ring, which contained the 0 element, which is the natural element for addition, which is stable under addition. So if you have two things inside of I0, you want the sum to be still in I0.
Yeah.
And you also want some absorbing property, which is if you take an element inside of your ring and you multiply it by any element inside of your ideal, you want the product to be inside of your ideal.
So, like, in any of those that don't remember what the ring is basically just like...
And the classical example of ideal are, for example, in Z, they are like multiple of a number.
Yeah, and basically a ring is just basically... we can think of it as sort of like I guess a space where, like, you can apply, like, two operations such as addition and multiplication, correct? That's, like, a good way to phrase it, right?
Yeah.
So then an ideal is basically... I guess like a certain type of ring that allows you to do certain that has special properties to it, right?
Yeah, so the reason why we care about ideals is we're able to do quotient where we can identify stuff. And quotient by I0 here will get us exactly what we want. We want the sequence that converge to the same point to be treated as if they were the same sequence in the first place. That's why we have to quotient out by I0. Are you still here, Peter? You had some kind of robotic voice.
Yeah, I'm still here.
Okay. I don't know if you can hear me clearly.
I can.
Okay, I'm having a little trouble to understand you, so I will write some stuff and hopefully things will get better. So today's goal will be to show that I0 is a maximal ideal. Cauchy in the ring of Cauchy sequence over the rational. And one consequence of that will be that as a corollary, so once we do that, we're going to set the real number to be equal to the set of Cauchy sequence modeled by I0. And one corollary from the ring course I gave you last week was that if you quotient out by a maximal ideal, then this guy is a field.
And basically a field is like an extension of a ring that has more properties in it, right?
Yeah, so you can also divide if you have a non-zero element of the ring, then you can find a multiplicative inverse.
Okay.
So divisions also makes sense, as long as you're not dividing by 0.
Okay.
All right. Okay. So first of all, we're gonna break the claim in two steps. So first of all, we have to show that I0 is an ideal. Okay. So first of all, we have to do a few things. So first of all, we're going to check that this thing is containing the
ideal.
It contains 0.
Okay.
We also have to check it's stable under addition. If AN and BN are two sequences that converge to 0, then we want the sum to be inside of 0. And okay, maybe this is not usually the way we do it, but we will also check that the subtraction is inside of 0. So the first two conditions just mean it's stable under addition. And the third condition is the absorbing property. So if we have AN, which is not necessarily a sequence that converges to 0, it's just a Cauchy sequence. And we have BN, which is something in I0, then we want the product of AN times BN to be also inside of I0.
Okay.
So those are the three things we have to check in order to see it's an ideal.
So basically, like if 0 is in the ideal, as well as the addition operations within the ideal is also basically from AN and BN are just random numbers, right? So we have to make sure that the operations involving multiplication and addition fit into that ideal, right?
Yeah.
Okay.
So for addition, we have to check if we take two things which is inside of our ideal, the sum and subtraction is still inside of the ideal.
And that's basically the property of an ideal itself, right?
Yeah, that's the definition. Those are the three things we have to check whenever we want to see that something is an ideal.
Okay.
So, okay, the first property is kind of obvious. So maybe... So, first it's kind of obvious because what is 0 in the case of a Cauchy sequence? This is just the ring where every coefficient is 0. It's the sequence where every term is 0.
Yeah.
So obviously the sequence which is always 0 is converging to 0. So first is obvious. Because the sequence given by AN is equal to 0 is obviously converging to 0. But this guy is by definition the 0 element of our ring.
So it's obvious because AN is equal to 0? Is that what you're saying?
Yeah. So maybe I can write the epsilon proof so that, I mean, if you're not convinced it's trivial, so I will just write the epsilon proof so you will see.
Yeah, I think it's like that moment in the book where in the textbook they basically said, obviously this means this.
Okay. So maybe I can show you using the epsilon proof. So let epsilon to be greater or equal to 0. For my big N, you can take whatever. So let's just big N to be any natural number. So usually usually in those kind of proof you have to choose N in terms of epsilon, but here we have so much freedom that we can choose N to be whatever we want. Okay, let little n be bigger than big N. Then what we have to show is that we have to show that the absolute value of AN is less than epsilon, right? That's our goal in order to show it's converging to 0. But that's definitely true because AN is equal to 0, right?
Yeah.
That's obviously true.
Oh, okay. So it all goes back to epsilon being greater than 0. That's why it's obvious. Okay.
Yeah. As AN is equal to 0, therefore we have 0 which is equal to AN.
It says that's obviously true, right? Is that what you wrote?
Yeah,
okay.
True. As AN is equal to 0 for every N. So first part was kind of easy. And the second part, the second part followed from the exercise from last week. is the exercise last week. So in last week exercise, I gave a few property of convergent sequence, which is if you have two convergent sequence, when you add them up, then you get you still get the convergence sequence, and the point where they converge is the sum. Okay, so maybe I would just recall. So if you have that AN is converging to A and you have that BN is converging to B, then in the exercise I ask you to show that AN plus BN is converging to A plus B. And also do for multiplication and subtraction. So 2 is just part of the exercise from last week. And the third one is probably the one which we're gonna have a little thing to show. So I will. So that's kind of funny because 2 was the exercise from last week. So the third one will, part of it will be part of the exercise of this week. But
I have still yet to do those, so we'll save those for the exercise portion.
Yeah. So maybe the third one. So I will show you where it comes from. So third one, it's enough to show the following. It is enough to show the following. Well, actually, the thing I will write in red is the thing you're gonna have to prove in this sheet, this week exercise. It's if AN is a bounded sequence, and BN is a sequence that converges to 0, then AN times BN is also converging to 0. Okay.
Okay. Let me just recheck on what the property is for 3. So basically, A is an element of the Cauchy to the rational numbers. B is an element of the ideal. Thus, A times B is an element of the ideal. Okay.
Yeah, and here the reason why this is enough. So here you might say, well, N here is not Cauchy, it's just bounded, right? But last time we showed that any Cauchy sequence is bounded. Therefore, this proposition applies in the case where AN is a Cauchy sequence, so you get the result. So actually, this proposition that I just put the black line on the left is a stronger condition than what I am than the thing we're asking to prove. But the fact the thing in black is the good proposition to prove. It's not really hard to do it, so I think it's a good exercise.
Okay.
Therefore, we've shown that I0 is an ideal.
Because it feels like we're trying to prove two things. It's like basically that AN is bounded and that B is also converging towards 0.
Yeah, but we already know that every Cauchy sequence is bounded. Therefore, the hypothesis that AN is bounded is already satisfied, right? Right. So if we assume that AN is Cauchy, then it's automatically bounded. Actually, Cauchy is a stronger condition than being bounded.
So basically, like I remember, like basically a Cauchy sequence converges, but what is the second property that is needed for the Cauchy?
So Cauchy sequence is, Cauchy sequence may not converge. For example, you saw last time the example I gave you for square root of 2 is not. It's not a converging sequence.
It's a Cauchy sequence, but it doesn't converge.
Yeah.
That's the one thing. So what are the conditions that we need to prove that it's Cauchy again?
So Cauchy is used. So maybe I can rewrite the definition. So AN is Cauchy. So it's like convergence if for all epsilon greater than or equal to 0, I'm able to find some rank such that for all rank which come after that, supposed to be P and Q, I'm sorry. Such that for all rank P and Q which are bigger than big N, I have that AN minus AP minus AQ is less or equal to epsilon. It's pretty similar as the definition for convergence. The only thing which is a little bit different is that we never we never use like at which point we converge, which is like the trick. We in the definition we only use our sequence. We don't use like an external point like in the case of a convergence sequence.
But this always goes back to like all P and Q, right?
Yeah, all P and Q which are bigger than our big N.
Okay, and that's basically how you prove that's Cauchy, right?
Yeah.
Okay.
So here I show that I0 is an ideal, but we want more because we want so if we just use the fact that I0 is an ideal, then I just know that the real numbers are a ring. But I can get much more than that if I'm able to show that I0 is maximal. Then I get that the real numbers is automatically a field, which is what I want.
Okay.
So step 2. Show that I0 is a maximal ideal. Say maximal. All right. Okay. And usually the strategy to show that something is maximal is to show that if you have an element which is outside of I0,
okay,
then automatically it has to be like I think this element will make the ideal like being the whole set. So we're gonna show that. But here I'm gonna show still a stronger result, and from this result, this property that I0 is maximal will follow.
Okay.
So here's a proposition that I'm gonna prove, and this proposition will be useful because it will enable us to define inequality for the real number after.
Okay.
Which is gonna be useful. So let's AN be a Cauchy sequence. Okay. And I want to assume that AN is not inside of I0.
All right.
Okay. Then there exists a sequence Bn which is also Cauchy, which is either one of those two which is either strictly positive or strictly negative. Well, I always forget. Doesn't English positive include 0 or not?
I don't think so. It could be, but I don't think it is because it's sort of like I guess a neutral number in that way.
Yeah, that's the thing that I always forget because in French, positive being it can also be equal to 0. So that's why I'm putting the word strictly.
Okay.
To forbid the case where it's equal to 0.
Maybe some cases it's appropriate to have it at 0. Positive, and maybe some cases it's not. So I guess. But I think
you're right because when people want to say strictly positive in English, they usually when they say they want to include 0, they usually they say it's not negative.
Yeah.
But in French, we would just say it's negative. It's strictly we would say it's negative because it's positive because positive for us already includes 0.
I think it's one of those cases where if you have a proof that it requires it to be 0, require it to be positive, then I guess you could do that. And I guess if it requires it to be negative, you could also put that there.
Yeah. So I don't want. So the important part is that I don't want any Bn to be equal to 0. I always want them to be strictly positive.
Okay.
Or strictly negative. I mean, just one of those.
Okay.
Okay. Okay, but then I just say I want some bn which has that. But what's related to our initial sequence? So what will relate to the initial sequence is that an minus bn will be an element of type 0. In other words, the sequence an minus bn will be converging to 0.
All right.
Okay.
Mm-hmm.
So if you think about the Cauchy sequence as being the real number quotient out by I0, this proposition is telling you that any non-zero real number will be either positive or negative.
Okay.
This is one way to interpret this statement. Okay, so maybe I can do a little bit of drawing so you can get the idea of the proof, and then I will go into the epsilon and inequality nightmare, but I will maybe draw you some nice pictures so you can get the idea.
Okay.
Okay, so here's a picture. Here's a picture of the proof. So basically the fact that our sequence is not converging to 0. Okay, so maybe I will write the rational line. So maybe we can write 0 as this point here. And the fact that our sequence is not converging to 0 would mean that we will be able to find some radius, some positive radius, which we're going to call epsilon, such that we're always able to find some elements or some elements outside of this radius.
Mm-hmm.
Okay.
Okay.
I mean, at least for n, which is bigger than. Well, maybe I should say for every. Well, I will be a bit more formal when I talk about. I write the formal proof, but for now I will just write something like that. It will exist some n bigger than n, such that we're able to find a point which is outside of that.
Okay.
And now we get so basically basically if you think about Cauchy sequence as something that should converge, basically what's gonna happen is this sequence is converging actually to a point, but it's just not a rational number. So it will converge to some quantity on the right.
Okay.
I mean, at least the way I draw it as if an was positive, but yeah, you get the idea. And how we're going to translate that in the proof is we're going to use the fact that our sequence is Cauchy. Therefore, if we go to high enough term, we should get that all the elements of our sequence will be stuck inside of some ball here. Okay. And so basically, for high enough term, every element of our sequence will be stuck inside of this ball. So maybe I will write something like for m. When you put something like that, it means big. It means large enough. Am will be inside of this ball. I don't know. Maybe we can call this ball B. This little will be inside of that. And the point of this ball is this ball will be strictly like all numbers inside of that will be strictly positive. Or negative. I mean, if the sequence is negative, but here it will be stuck here. Okay. But as we already mentioned a few times, the notion of convergence and Cauchy sequence doesn't care about the first term, right? So the first term, I mean, as I said, they are always troublemaker, right?
Yeah.
Even if the sequence here seems to like, I mean, almost every point, every term of sequence is stuck inside of this green ball, we still have to deal with the first term, which can be a very
it could be like way outside of the radius.
Yeah, A1 could be there, A2 could be there, A3 could be chilling inside of this ball, which is the forbidden zone. So those guys will be kind of the thing we have to take care of them. Okay. So what we're gonna do is we're gonna say, okay, maybe Okay, maybe we can say maybe in for n bigger than n0. I don't know. Maybe we can say when we reach the index n0, every time we'll be stuck inside of this green ball. Okay.
Okay.
And what we're gonna do is we're gonna replace all the terms that come before them, before n0.
Mm-hmm.
But n0 is fixed, so we just have a finite number of them.
Uh-huh.
And so what we're gonna do is we're gonna basically define the sequence bn to be equal to 1 if n is strictly less than n0, and otherwise we put an here if n is bigger or equal to n0. So this condition will ensure that the bn will be strictly positive.
Okay.
Okay.
Uh-huh.
So we're kind of using the fact that those troublemaker at the start can do very like funky stuff and being like everywhere, but we can also be a little bit silly and just put 1 for every. We can just put some garbage value at for the first value, which verify the function we want, and we will get then the an minus bn are still going to 0. Because for high enough term, then they become equal, right?
Okay, so let's say like for what you set up here, bn is equal to 1 if n is less than big N 0, right?
Yeah.
So let's say you said it's a finite amount of terms, so let's say the finite amount of terms, let's say 5, right? Does that mean like if it's like b1, b2, b3, b4, b5, like that would just those terms would just be 1, right? And
yeah,
then,
exactly.
Yeah, and then if it's like say n, let's say b6, right? Then we would be like an at that point, and then afterwards it would be all an, right?
Yeah, exactly.
Okay.
So the point is that the high enough term are well behaved, but the one that come before that are very bad behaved.
Yeah.
But as the notion of convergence and Cauchy sequence only care about what happened later, then we can just put some trash value at the beginning to make our make our proposition. Okay.
Mm-hmm.
So at least I hope my drawing was a bit. I give you an idea what's gonna happen. Now
I've seen that example in textbooks a lot. I'm guessing you set it to 1 because it's just much easier to deal with than just. Like,
Yeah.
Okay.
Yeah. Okay. Proof.
Okay.
So we know that n is not converging to 0, right?
Mm-hmm.
That's one of the given. So what does it mean formally? So if it was converging to 0, it means that for every epsilon we should be able to find some big N such that for all ranks that go beyond that, the absolute value of an should be less than epsilon.
Okay.
So if an failed to be equal to 0, it means that there is some epsilon which the condition will fail. Therefore, there should exist an epsilon greater or equal to 0. Okay. By the way, that's a good exercise to write what is the negation of the statement that n is converging to 0. This is what I will write then.
Are you saying that's a good habit to basically write for proofs within real analysis? Is like.
Yeah. So usually when you start proof writing, it's a bit sometimes hard for beginners to be able to write what is the negation of the statement. But this one is a good example because it's not a very trivial one to write out.
So if it involves a Cauchy sequence, basically. Like say like an is not converging to 0 and there exists an epsilon that's greater than 0. So basically like if it involves a Cauchy sequence, just write that automatically as part of the proof, right?
Yeah. And basically what you're gonna see is that I have quantifier like there exists and for all. And when I negate a statement like that, all the quantifier will be inverse.
Okay.
So my for all epsilon become there exists an epsilon.
Okay.
And usually the last thing I will write on the right would be there exists some big N, right?
Okay.
Here, if I do the negation, it's going to be for all big N, which are bigger or equal to 0.
Okay.
And so usually the third quantifier would be for all, right? For all little n which are bigger than n, we have something, right?
Yeah.
But here, as doing the negation, I will just have there exists. There exists some n, which are bigger than n, such that, and on the condition would be that an. So usually the statement would be that an is less or equal to epsilon. So the opposite. So the negation of the statement is that an is bigger or equal to epsilon.
Okay.
Absolute value of an. Okay.
Okay.
Okay. There's a thing that I didn't think of it, but I guess I will just move on and we'll see if I'm able to fix the proof.
Okay.
Okay, so this is the fact that n is not converging to 0, but if it wasn't converging to 0, it could be a lot of things, right?
Yeah.
For example, maybe we have this sequence, so maybe I will write something on the right, which is not part of the proof, but just like some indication of what might happen.
So it's a side note, right?
Yeah. So we might have a sequence that looks something like that.
Okay.
Well, actually, we could even use an is equal to n, right?
Yeah, I guess so.
Yeah. Oh, actually, I want to put a -1. Okay. So basically, if I just draw, just intuitively, what's going to happen is that I have 0 here, and now this sequence is going to sort of dance from right to left, right? So A1 would be, well, I guess A0 would be somewhere. No, A0 would be 0, but okay. A1 will be somewhere there. A2 will be, I guess they're not very. Sorry about that. I will redraw the thing. Okay, so basically it would look something like that. A1 is here, A2 would be 2 here, A3 will be there. And A4 is there, and you kind of see that the sequence is kind of going outward, right?
Yeah.
Flipping between being positive and being negative. And this sequence will not have the property that I want, right?
Yeah.
Because half the time it's positive and the other half is negative.
Yeah.
So those kind of sequence wouldn't work. But this sequence is not Cauchy. It's clearly like the distance between 2 points getting bigger and bigger at every step. So this guy is definitely not a Cauchy sequence.
Yeah.
So I would have to use the fact that my sequence is Cauchy. That's the thing I should probably do as my second step.
Okay.
So okay. So first of all, I want this ball on green, so I put it as if it were like after the red part, right? The red ball. But actually, I don't. It could be in the middle, but the only important thing is that it's not. It does not contain 0, right?
Yeah.
So it could be like, it could have been like somewhere there. It's fine.
Yeah.
So what we're gonna do is we're gonna use the fact that an is Cauchy. As an is Cauchy. And now I'm gonna use the epsilon that I have here. I'm gonna use an epsilon and a half.
Okay.
Using the one above. As n is Cauchy, there will exist some rank, big N, bigger or equal to 0, such that all the rank that go after it. Okay. Sorry, I'm supposed to put P and Q. I'll always forget about those. All right. For all P and Q, which are bigger or equal to N, we have that the distance between AP and minus AQ is less than an epsilon and a half. Okay.
Okay.
So maybe here I will maybe broke down some properties. So maybe this property I will call it star.
Okay.
And this guy I will call it double star because I'm very good at naming stuff, I guess.
Okay.
And so what we're gonna do is let peak n bigger than big N. So the big N here is the one here. That verifies star. Namely, AN is strictly bigger than epsilon. The absolute value of AN is strictly bigger than epsilon. Mm-hmm. Okay, so the star is just the fact that AN is not converging to 0, so I should be able to find that. So we're gonna use this guy, okay?
Mm-hmm.
Okay. So okay, here's the deal. Okay.
Mm-hmm.
Okay. First of all, I'm gonna split here the proof in 2 steps, but we're just gonna do 1 step because the other will be similar. Okay. So this tells you that the absolute value of AN is bigger than epsilon, right? But this is equivalent to say that
AN is oh no, I was gonna split it into like negative epsilon and AN.
Yeah.
That sequence. Well, not sequence, but that way of writing it.
Yeah, you could write it like something like that. Well, actually, it would be 2 inequalities, so. So AN is either less than minus epsilon or AN is bigger than epsilon, right? Those are like the 2 possibilities.
Yeah.
And what I'm gonna do is I'm gonna assume that we're in the second case. Okay. The reason why I'm able to do that is because if we're in the first case, I could just change my sequence by the same thing, but that I just multiply by -1.
Yeah.
And now I get myself into the second case, and basically, so basically the case that I'm not doing, you can recover from the case I'm doing. So I will just not bother with it. I will just do the second one.
Mm-hmm.
So. In English, we like something like, without loss of generality, we may assume that AN is bigger than epsilon. Okay?
Okay.
And now, so now what I claim that for all n which are big or equal to my big N I'm above, I have. Oh shoot! I shouldn't call this guy AN and those guy AN. I guess I'm gonna call that M instead of N. Okay. I have that AM is bigger than epsilon and a half.
Okay.
Okay. So maybe here I can maybe show you the picture. So here I have the epsilon ball. I have the famous AN, which is outside of the epsilon ball. And now I said that I'm considering a ball which is less than epsilon and a half, right?
Mm-hmm.
So so this condition is less than epsilon and a half. Mm-hmm. So what I will do is I will consider this ball. Okay. Which is of radius epsilon and a half. Yeah, maybe the drawing is not at scale, but you get the point.
Yeah.
And basically, I know that all the AM will be stuck inside of this region.
Mm-hmm.
Okay. And the point is that the border of the okay, my drawing is really not at scale, so I apologize. The point is that epsilon over half will be somewhere there.
Uh-huh.
And so all the points in the blue region will be bigger than epsilon and a half.
Okay.
Because of that.
Uh-huh.
Okay.
Mm-hmm.
So this is the picture. Now we'll write the thing here properly. So let's use double star.
Okay.
So let's m be bigger or equal to n, and let's apply double star. So double star, what it tells you that the distance between AM and minus AN is less than or equal to an epsilon and a half. Okay.
Okay.
Are you still there, Peter?
Yeah, I'm still here.
Okay, Kim. Observe in particular. So this inequality alone already implies that AM has to be strictly positive. Okay. Because we know that AN is bigger than epsilon, and we know that the distance between AN and AM is less than epsilon over 2. Well, I guess I don't have to write that. Maybe I can not do like that. Okay. Okay. I guess I need the part to show it's positive, but okay. So we get a double star, we get this inequality.
Uh-huh.
And now we're gonna play a little bit, okay? So I would like to have some bound on my AM. Okay, that's the thing I care. So I care about absolute value of AM, okay?
Uh-huh.
I would like to know it's less than some quantity, okay?
Uh-huh.
And I'm gonna use the triangle inequality. So how I'm gonna use the triangle inequality is that I know that AN can be written as so again we're gonna use some clever writing. We're gonna write something like that. AN minus AM, and then we're gonna add the thing we just removed it. Okay.
Okay.
That's still good.
Yeah.
And now we have like a sum of two things, so we can use the triangle inequality on that.
Yep.
We got AN minus AM plus absolute value of AM. Okay.
Uh-huh.
But now we can use the different bounds that we have. So we know that AN is absolute value of AN is bigger than epsilon.
Yeah.
So we get this epsilon over there.
Uh-huh.
And this guy is less than epsilon over 2.
Yeah.
So we can write something like that. Epsilon over 2 plus AM. So if I write it in clear, we have epsilon is less than, well, I guess it's supposed to be strictly less than epsilon over 2 plus absolute value of AM, which is the thing I care.
Uh-huh.
Okay. And now what we can do is we can just use the algebra.
Okay.
So I will just subtract by an epsilon over 2 from both sides. So as usual for inequality, if I add stuff from both sides, the inequality still holds, and if I subtract stuff from both sides, the inequality still holds.
Okay.
Okay.
All right.
So if I subscribe by epsilon over 2 from both sides, I will end up with epsilon over 2 is less than the absolute value of AM. Okay.
Yeah.
And we can also use as the absolute value of AN minus AM is less or equal to epsilon over 2, and the fact that AM itself is strictly bigger than epsilon, we can actually oops, sorry, this is supposed to be an AN. We actually have that AM is also positive. Of the absolute value because the quantity is positive. Okay.
So what I see is that you wrote. Oh, okay. Now it came up. I was about to say, is greater than 0, and that epsilon over 2 is less than AM, right?
Yeah.
Okay.
Okay. So now we know that. So what we showed is that we showed that for every. We showed. That for every little n which is bigger than n, we have epsilon over 2, which is a bound from below from n. Okay. And now we're gonna apply the strategy that I told you before. Okay. Now we're gonna set Bn to be equal to 1 if n is less than n, and An if n is bigger or equal to big N. Okay?
Okay.
And now we'll just state some obvious facts, but what you can see is that Bn is Cauchy. Why is that?
Let's see. Bn is a Cauchy. Because basically, there has to exist an n, like a small n bigger than n, and basically it has to be greater than epsilon. Like basically, you know, like we have like say like let's say BP minus BQ, that would have to be greater than epsilon, and basically like you wrote like epsilon over 2 is less than is that AN or AM?
AM.
AM?
Yeah.
Okay, AM. So basically, like, it's still greater than epsilon at that point.
Yeah, but that's not really the reason why. The reason why is because if you look carefully at this definition, when n is bigger than big N,
it basically becomes AN.
AN, but we know that AN is Cauchy by hypothesis, right?
Uh-huh.
Therefore, Bn is also Cauchy. Bn is Cauchy because AN is Cauchy. Okay?
Uh-huh.
And maybe I can write this triple star.
Okay.
And from triple star, it follows that Bn is strictly positive. From triple star, Bn is strictly positive. Is that good, Peter?
Uh-huh. Yeah, I still see it. Yeah.
So as I said, those guys are the troublemaker when they're less than big N, but But as the notion of a Cauchy sequence doesn't care about what's happening at the beginning, we can also be a little bit clever and put some positive content.
Yeah, when you asked, I was thinking of the definition of Cauchy, and I was like, oh, like I didn't go back to like what we just written before, so that's why like I couldn't like really like answer it, because I was like, wait, I have to think about the definition of a Cauchy, and then I was like, and then I didn't think about what we just did before, so.
Yeah. Okay, so this showed the claim. Okay, so to summarize, if we have a Cauchy sequence which is not converging to 0, then we can find another Cauchy sequence which terms are strictly positive or strictly negative, such that the difference between our initial Cauchy sequence is a sequence that goes to 0, right? That was the proposition that we just proved.
Okay.
Okay, if we go back to the top, an minus bn is going to 0. Okay. And now we're gonna show. So I'm gonna teach you. I'm gonna show you why this implies maximality of I0.
Okay.
So consequence. I0 is maximal. And you sort of see how those proofs kind of go usually. So usually what you assume is you assume otherwise. Assume otherwise. So if it's not maximal, then it means that I0 is setting between some maximal ideal M and the entire ring, right? I mean, like in the way I'm writing the inclusion. Yeah, something like that, right?
So, oh, okay. That's supposed to say Cauchy, right? Cauchy of Q?
Yeah.
Okay.
Where M is a maximal ideal.
Okay.
And from that, we're gonna try to derive a contradiction. Usually the thing that we saw in the polynomial example and the integer example I gave you last time is usually the strategy is to show that 1 is inside of M.
Okay.
Because if 1 is inside of M, then by the absorbing property, M has to be the whole ring, which is not possible because maximal ideal are supposed to be proper subset of the ring.
Okay.
Okay. So we're gonna do that. So assume otherwise. Therefore, they're gonna exist some sequence xn inside of M, such that xn is not inside of I0. Okay.
Okay.
By the previous properties, by the previous proposition. Okay, maybe I will call it AN, so we can really have the same notation as I had before. I can find. Sorry, this is supposed to be an AN. I can, by the previous proposition, I can find BN, which is strictly positive or negative, such that AN minus BN is converging to 0. Okay? So what does it imply? It implied that so what's going to happen is that hold up. Yeah, okay. Look what's gonna happen. So we know that N is inside of M, right? This equals inside of M, and we know that AN minus BN is going to 0. In other words, that the sequence AN minus BN is inside of I0, right? By definition. But as I0 is contained inside of M, we also know that AN minus BN has to be has to be, maybe I will write the other way around, I'm sorry. I'll write Bn minus An. It doesn't change much, but it's just going to be a little bit easier in terms of writing. Okay, we have this, okay? Therefore, Bn minus An also has to be inside of M, right? Because Bn minus En, this sequence is also an element of M. But then M is an ideal, therefore I can add them, right?
Yeah.
So if I add those two sequences together, I end up having that Bn, the sequence Bn is inside of M. Okay?
Okay.
But as Bn, so this is one of the properties. Maybe I skip actually the proof of that, but it's not hard. It's quite similar. You have an exercise from last week which is very similar, showing that if you have two convergent sequence and the bottom is never, and the second sequence is never 0, then the sequence An minus Bn is convergent, and it's convergent to A over B if A is the limit of An and B is the limit of Bn. Okay. So this is just like a algebra of limit, and you can show the same thing for Cauchy. If you have two Cauchy sequence and you look at at the division of those two, and the denominator is never 0, then the thing you get is indeed a Cauchy sequence.
Okay.
So what's gonna happen is that Bn is never 0. For all n. Therefore, 1 over Bn is also Cauchy. Okay.
Okay.
And this would be a problem because if 1 over Bn is Cauchy, then it means I can multiply the two together, right?
Yeah.
So I would have Bn times 1 over Bn. This sequence will just be the sequence which is equal to 1.
Yeah.
Therefore, the sequence which is always 1 is inside of the ideal M. But this contradicts the fact that M is maximal, thus proper subset of Cauchy. And then we're done. Okay, so maybe here I haven't spilled all the detail, but it's the same thing we saw last time. If you get 1 inside of your ideal, then you're kind of doomed because you will have to contain the entire ring because
so the last thing you wrote is but this contradicts the fact that M is maximal, and what's after maximal?
Does a proper subset of Cauchy Q.
Oh, thus, okay.
Yeah.
Proper.
So it's the same trouble that we saw last time. If you have 1 inside of your ideal, then you're kind of doomed. You have to be the whole ring.
Okay, so basically 1 over B is Cauchy. Is it because just Bn is Cauchy? Is that?
Yeah. So here I use the fact that Bn is Cauchy and the fact that Bn is never 0.
And because we're assuming that they're Cauchy within the rational numbers, thus that's why you can have 1 over B n in this case, right? Because they're in the same they're mapping towards the rational numbers, right?
Yeah. So if Bn is a rational, then 1 over Bn is also a rational.
Okay, so you can just basically just say like, hey, there's this one number, but that's just leading to your point that they contradict because if you were to multiply Bn times 1 over Bn, that would equal 1, which is what you're trying to show that it's not in that case. Okay, so this is proof by contradiction mainly.
Yeah. I started the proof by assume otherwise. So assume otherwise, and you have that I0 is less than some proper ideal, and then I derive a contradiction that M was not proper.
So remind me, like, what are the, like, how do we show something is maximal again?
So basically, that's the way we show that something is maximal. Most of the time you use a proof by contradiction like that.
Yeah.
So here what I did is I assumed that I0 was not maximal, so we can find an ideal which is bigger than M, the I0.
Uh-huh.
But then I showed that this ideal has to be not proper, so therefore I0 has to be maximal.
Because there's a because like I remember the last time we talked about the difference between a maximum and a maximal. And
yeah.
I'm trying to remember exactly what was the pure definition of a maximal.
So maximal just means, so for every comparable subset, for ideal, maybe like you cannot always compare them, right?
Yeah.
For example, you cannot compare the multiple of 2 and the multiple of 3 because none of those ideals is contained inside of the other, right?
Okay.
So it does not make sense to say that the multiple of 2 are bigger than the multiple of 3. They're both like...
Okay.
There is no like a subset relation between the two. And but sometimes you can, right? So for example, if you have the multiple of 4,
yeah,
then this is a proper subset of the multiple of 2, right?
Yeah.
Because if you divide 4, then you have to divide 2. So
yeah,
those guys. So you can say that the multiple of 2 is a bigger ideal than the multiple of 4.
Mm-hmm.
And basically, so basically, maximal just means among all the ideal that you can compare with.
Yeah.
You're the biggest.
Okay.
But I mean, as the example I showed you with the multiple of 2 and multiple of 3, you might not be able to compare every ideal between each others.
Okay.
And maximum just basically mean that in the case of subset or ideal, usually you don't have maximum because you rarely have the case where you have a maximum because that's kind of a strong condition. Your ring has to be something very special to happen.
Okay.
Which it can happen with.
I can also go back to our previous lecture on that as well because I recorded it. So yeah, I'll definitely re-review that. Yeah.
So now we're kind of happy because what we have now so far, we have that R is a field. So that's pretty good.
Okay. R is a field. So the previous proof, like how many proofs did we do? Did we do like 2 proofs or did we did 1 whole proof? Or did we do more than that?
So we proved 1 big result, but we had like some
it looks
scaffolding involved at some point.
Yeah, I think we count 3. It looks like because I see 3 empty boxes. Yeah. So we used 3 proofs to basically show that the Cauchy of the rational numbers is not that has something within it that basically is not the rational numbers. Basically, that's what we're showing, right?
Yeah, so what we show is that, so I want to define R to be the sequence of Cauchy sequence. Because as we saw last time, they're able to see numbers which are supposed to be there, but they are not, like for example, square root of 2.
Yeah.
But we couldn't really take that as a definition because otherwise we had like a lot of duplicate, right?
Yeah, because we don't know if that, that Cauchy of the rational numbers is infinite or is it like a finite number that we can just include in there, right? So that's why we did all this, right?
Well, this was, all we did today was to show that I0 was maximal. To get that R is a field for free.
Okay.
But now we did it. We have the real numbers.
Yeah.
So
basically, you're just showing us that basically like the real numbers are just the Cauchy of the rational numbers divided by an ideal.
Yeah.
Okay.
That makes sure we don't have duplicates.
Yeah. Okay. So in this case, how should we think of the ideal? Because like I think with Cauchy, it's kind of, I wouldn't say it's obvious, but it's kind of like if you think about it, it kind of is there because obviously like we know that the Cauchy for the rational numbers is not, it doesn't converge. But for the ideal, right? Like for me, I'm thinking of it as just like, I know it's not a number or anything, but how should we think of it so that we can better visualize that, oh, this is obviously the real, leading to the real numbers?
So this guy is an equivalence relation.
Okay, so it's an equivalent relation.
The way you want the equivalence relation, and the way you want to think about it is that, as the example I showed you earlier, is that for example, if you want to represent 0, if you just take the Cauchy sequence, then there is a lot of Cauchy sequence that represent 0, right? For example, I can take an which is equal to 0, that's the obvious one.
Yeah.
But I can also take the sequence 1 over n, right?
Yeah.
Okay, maybe I will take a better example. Okay, for example, I want to represent 1, I can take the sequence which is constantly equal to 1. And if I want to represent 1, I can also choose something else. I could choose, for example, 1 plus 1 over n. That would be a good choice. I mean, if I want to be a little bit funky, I could choose 1 over 2n, right? So if we have chosen R to be the Cauchy sequence, then we will be in trouble because all those three things are different as sequences.
Yeah.
And the thing that we are dividing by, just make sure that those three will be equivalent. Okay. So here the reason why an is bn are equivalent is because if I do an minus bn, so this guy will be 1 minus 1 plus 1 over n, so we get minus 1 over n, right? When I do the difference between the two, I get that this guy is converging to 0, right?
Yeah.
And this is exactly what the quotient by I0 is doing. It said that if you have two sequences whose difference is a sequence that converges to 0, then those two sequences are equivalent.
Okay, so let's see. I'm just recapping here. That would converge to 0. So you're basically saying that the ideal basically makes the, I guess, any scenario, whether it be AN, BN, or CN, that they're all basically the same type of relationship, as it were.
Yeah, so the point is that those three sequences are all converging to 1, right? If we were only considering them as Cauchy sequence, then those three sequences would be different.
Oh, so basically, this is the way I'm summarizing it in my head, and you can tell me if I'm wrong, but
yeah,
you're basically saying that whatever, let's say if it's like within the rational numbers, right? Any number that basically, like any number that's within that set, basically there's different ways of getting to that number, right? Like, you know.
Yeah, exactly.
And like, so the different ways of getting that number are all the equivalence relations. So basically the Cauchy of the rational numbers over the ideal. The ideal is basically saying all the ways you can get those specific numbers within that particular set.
Yeah.
Okay.
I mean, basically it say I will consider those sequences to be equal if their difference is something that goes to 0.
Okay.
It's pretty much like, you know, like even an odd number, right?
Yeah.
Like I will say that 3 and, for example, 5 have the same parity if their difference is an even integer, right? So this guy will be a -2, which is an element of 2z.
Okay.
So it means like when we do the quotient z minus 2z, then those two numbers will be equal in the quotient. Because their difference is an even integers.
Okay, so basically the ideal is just basically saying, hey, regardless of what operations you're putting into, they're all going to equate to the same number that you're thinking of in this case.
Yeah. So if you have, so maybe that's the thing we can show, that if we have a sequence of, if we have two sequences of rational number which are convergent and goes to the same number, then in the real number they will be the same number.
So is this
okay.
So like basically like going back to things that we learned in Calc 2, right? Is this why they teach you sequences before series? Like when you think about like sequences, there you can think of them as sort of like basically it's like before you come up with the equation, but when you come up with the equation, then all you have to do to turn it into a series is just basically the summation symbol in front.
Yeah, so series are just a special case of sequence.
Okay.
And I assume they probably teach you that first in calculus because a lot of tests to checking that a series is converging is pretty much looking at what's
and this is why they keep telling you like basically, okay, think of the formula that equates to this sequence. Because you're technically creating a series, you're technically creating like the first part of the series, and the only thing you need to complete is just the summation symbol.
Yeah.
Okay, gotcha.
So here maybe that's a very strange thing to define the real number as I mean, I think among like all the things we define, like we started with, with the natural number.
Yeah.
So I mean, I think among the weirdest thing that we define, I think the natural number are kind of weird because we start with empty set and we like build our way up, which is probably not the more intuitive way. But I think like going from the natural number to the integer is not that bad, and the integers to the rational, I think it's a pretty natural. I mean, I think that's the most like reasonable thing you could have thought is going from the integer to the rational.
I kind of think of it as the opposite, because when you think of the natural numbers, it's easier to make it out of nothing, which is the empty set. But then like when you go into more into the like the integers and the empty set, you have to think of things like relations and rings and all that stuff, and I'm like, oh, that it's very intricate. So for me it's like it's kind of the opposite, but I guess for you it makes more sense because it gives more foundation of where those numbers come from.
Yeah, I mean, we could have avoided the ring language, but the problem of avoiding the ring language is whenever we have inclusion.
Yeah. No, I think it makes it more simpler because it kind of gets you into, I think, like what makes math like a little bit more interesting, because then you learn things like, more of the abstract algebra without having to have, like, you have to go through a prerequisite to know what abstract algebra is, like within a group, I think.
Yes. So basically the reason why we did have rings is because, I mean, if we haven't used rings, we would basically have like the natural number, the integer, the rational, and the real numbers are just sets. Yeah. And we sort of wouldn't have like considered the arithmetic on them. Like we would, I mean, ring is more than a set. It's a set with more properties, right? It has addition, it has multiplication.
It's practically like an arena where basically certain rules can be done. I don't want to say space because I don't want us to get confused with a mathematical space. Yeah. But it feels that way.
Yeah, so you sort of have more structure, and I mean, using the language of ring, you can sort of see what is preserved when you go from the rational to the real number. Like, is the addition like similar, or is that something completely different? And
you usually learn that in abstract algebra mainly, right? Like rings and fields and all that stuff, right?
Yeah. Usually they don't do this example of going from.
No, I think this is good. I think this is good because it's sort of like a more. Yeah, it's kind of a way to get your feet wet in like different areas of math besides like thinking of them as just purely sets, because I never thought about the operations that go into each set, and I'm like, oh yeah, you're right, we haven't proven that this arithmetic works. Yeah. So I think this way is much better because it's like it shows us, oh, the arithmetic works because of this particular property or this particular definition.
Yeah, for example, the inclusion of the integers inside of the rational number, well, if you just consider them as set, then I guess you could embed the integers in like a lot of ways inside of the rational number.
And it makes more sense because it gives you more rules to the game, because it's like, oh yeah, we have rings and we have fields, and like, I mean, we did more with Cauchy than I think like probably like you would probably learn in real analysis, right? Like we probably put more emphasis on like, I think like the importance of Cauchy with like more complicated like scenarios, like with rings and with ideals.
Yeah, I mean, this conversation is sometimes done in the first course in real analysis, but yeah. I mean, there's kind of two ways to build a real number, and basically you have, there's like kind of two constructions you can use to build a real number. I mean, very well-known construction. You have the Cauchy sequence construction, that's the one we just did, and there is also the Dedekind cut construction that also works.
Oh, okay. All right. So what's next?
But yeah. I mean, sometimes in real analysis, they will skip the construction of the real number altogether. But I think it's important to do it because otherwise...
That way we know what exactly what it is. Okay, so...
Yeah. No, we know exactly what it is. It's kind of a...
No, I mean, it's a good way to think of it because it's sort of like, you're not thinking of it as just a set. You're thinking of it as sort of like, oh, this is a set with a certain... I'm not going to say it's a certain formula, but it kind of feels that way because it's sort of like, it's a Cauchy of the rational numbers plus, divided by the actual ways of you getting a single number, different methods of getting that same similar number or particular term if you want. In that case,
yeah. Okay, now I want to discuss a little bit about R. So if we would have done without ring theory, we would just have this is a set, but now we know it's a field. But we're still missing a few important ingredients on the real number.
Okay.
Namely, we should have a notion of distance.
Okay. Yeah.
And also, that will be something we're gonna do for the next weeks. Is that we're gonna talk a little bit about the topology of the real number, but for that we need a notion of distance first.
Okay.
Okay. So. Okay. So I will use. Okay, maybe I will use a proposition, but we basically prove this proposition. Okay.
All right.
So from now on, I will think of for now at least, I will think of real number as a equivalence class of Cauchy sequence. Okay.
Okay.
So if an is not inside of I0,
all right.
Namely, an is not going to 0, so it's not 0. Then the class, or maybe I should have write the class, but the equivalence class an. Contain a sequence Bn which is either strictly positive or negative, and if Cn is another such sequence, so I mean that Cn is also strictly positive or strictly negative, then Bn and Cn have the same sign. Sorry.
So if Cn is what is that after? Is a blank that...
no, he's missing a word. It's no sequence.
Oh, okay.
So I should say Cn is inside of the same equivalence class.
Oh, okay.
So what is this proposition saying? It's saying that if the equivalence class of n, you should think of them as a real number. So if a real number is not 0, then it's either positive or negative.
Okay.
That's what we're trying to make sense of it, and that's pretty much what this proposition is saying. And from now on, we will say.
So Bn and Cn are supposed to be in An?
Yeah.
Okay.
Yeah. So Bn and Cn are Cauchy sequences which are equivalent to An.
Okay.
So the difference between An and Bn is 0, and the difference between An and Cn is also a sequence of convergence. we will say that an is a positive. I guess I will use the English word because otherwise I would confuse you. Is a positive real number if Bn is positive, and I mean we will say the same thing for the other case. So an is negative. If Bn is negative. Okay.
Okay.
So proof. So we already went through the proof of the first part. We have already proved that such a Bn exists. When we prove it was maximal, I prove actually the first part of this statement. That we're able to find a Bn which is either strictly positive or strictly negative.
Mm-hmm.
Okay?
Okay.
And that's the reason why basically I proved the stronger result before, is because I knew that I had to prove this at some point. So we already have the force, we already know that such Bn exists, okay, so we have existence.
Mm-hmm.
Now we have to show that if Cn is another such sequence, if Cn is another such sequence, then Cn and Bn have the same sign. So we just have to show the sign condition. Okay?
Okay. Okay.
And basic.
Mm-hmm.
So you good?
Yeah.
Okay, let me think about it something.
So you wrote if Cn is an that's such a sequence. Is that what you wrote?
Yeah. Is another such sequence? I don't think that's the proper wording, but I just want to say that Cn satisfies the same property as Bn.
Okay.
But we don't know what is this sign. Okay, maybe I want to go back to a proof we did earlier because I think we can get a stronger condition. Okay.
Okay.
Yeah, my bad. Okay, I will change something. Okay.
Okay. Yeah.
So, are you following me right now?
Yeah, I'm following you.
Okay, here I think I can strengthen this proposition. So instead of saying it's strictly positive or strictly negative, we're gonna say that n is bigger or equal to an epsilon over 2.
Okay.
Or less than minus an epsilon over 2, okay? And so this is maybe a stronger statement, but I can change it really easily in the proof. So to get that from the proof I wrote, I just need to so are you following me?
Yeah. So you said an is either greater than epsilon over 2, or an is less than negative epsilon over 2, or just
yeah.
Okay.
Negative epsilon over 2. And to fix the proof that I show you, so to be able to get this result. So are you following me?
Yes.
I will just change the 1 here by epsilon over 2, and then here I will put the plus 1.
Okay.
So I mean, if we just go back at the proof, so this should now works. Because I already know that if little n is bigger than big N, then I know the condition holds. And otherwise, I can just put whatever value I want. So I will just make sure that I choose something which is bigger or equal to epsilon over 2. So I will choose epsilon plus 1 over 2.
Okay.
Okay. I will need this stronger condition. Okay.
Okay.
Okay. So we already know that those things are equal. And now what we're gonna do is we're gonna show that. So we just have to show that Cn and Bn have the same sign. Okay, maybe here I will just change the statement. So this is another such sequence. Then we want to show that Cn and Bn have the same sign. Okay.
Okay.
Okay, I didn't prepare the proof, so it might be a mess, but let's do it.
Okay.
So I guess like what we can do is we can assume otherwise. Okay.
Okay.
Assume otherwise. I think by contradiction this proof would be easier. Okay.
Okay.
So by the previous lemma, by the previous proposition, I mean one of the previous proposition, maybe the previous proposition is not the right word, but I think you get what I mean. We can assume there exists an epsilon bigger or equal to 0, such that So let's maybe take Cn to be negative and Bn to be positive. I mean, it doesn't really matter. So we're gonna assume that Bn is less than minus. Well, I guess we can just put minus epsilon. And Cn is bigger than epsilon. Okay.
Okay.
Well, I guess I did backward with what I said, but whatever. And now we want the contradiction, okay?
Okay.
So what we're gonna do is we're gonna look at the sequence Bn minus Cn.
Okay.
Let's have a look at Bn minus Cn. Okay. So this condition that Bn is less than minus epsilon, and the condition that Cn is bigger than epsilon. Just mean that the absolute value of Bn is bigger than epsilon, and the absolute value of Cn is bigger than epsilon. Right? Okay. Now we need a clever way to get a bound on that guy. Okay.
Okay.
I don't think I want to use that. I think I want to use the thing that I wrote earlier. Okay. Okay. So what we're gonna do is we're gonna use those two guys to get the bound I want.
Okay.
What is simpler? I think it's better to write. Okay. So I want the bound Cn minus Bn. But as Cn is positive and Bn is negative, I can just remove the absolute value, right? Because anyway, Bn will be negative, so if we put a minus in front of that, it will be this is negative.
Yeah.
Okay. So what do we get from that? So we get that. So Cn minus Bn. Okay, so we know that Cn is less than epsilon, and let's maybe put a minus in front of the Bn here.
Okay.
So if we put a minus, then we're gonna swap the inequality sign, right?
Okay.
So we're gonna get epsilon is greater or equal to minus Bn. Oh shoot, no, I'm doing a mistake. Sorry. The opposite.
Yeah, I was about to say that doesn't look right.
Yeah. Yeah. Okay. This is right. Okay. Okay. And then we get into trouble because now I would have Cn minus Bn. So what I did is I just add Cn and I added minus Bn, right?
Okay.
But I know that Cn is less than epsilon, and I also know that minus Bn is less than epsilon. Oh no. No, I lose my screen.
Oh, you lost your screen? Yeah, because I noticed some parts were missing when you were writing, because it was supposed to be like Cn minus Bn, right?
Oh no, we get the time of the stream where the escalator is just dying on us.
Yeah.
Okay, so I'm back, but I don't see it. So what do you have here written?
Basically what you have. I think if you go a little bit lower.
So can you draw me like a line where I can draw?
So anything under this line, there's nothing written.
Hold up, I don't see your line. I guess I will refresh my page. Following. Okay, where are you?
You're like.
Oh,
You're like. I'm like way below. Yeah.
Well, I guess go where I'm supposed to write, and I will write under it.
Yeah, because like I see them writing from the previous stuff. Do you want to start a new one? Because there's a lot of writing.
Yeah. We could start a new one.
Okay. Let me just over here. Everything's recorded, guys. So we basically. So basically, we can go back to the videos and look at what we wrote. So where is that button to? I want to make a new one. Fine. No. Like I'm totally wilding out. I don't remember which button it is to reset. Let me just refresh. We just start that. Because I remember there was a button that allowed you to refresh the page. Alright, let's just click stop session. There we go, reset canvas. There we go. Just copy that. And I'll send it to you.
Right.
Alright, there we go.
Okay, so sorry for the missing part.
Yeah, sorry about that, guys. But
so what we had like Cn is bigger than epsilon, I think. And we had that.
Yeah, epsilon is less than
something like that.
Yeah, it's less than Cn, and epsilon is greater than Bn, negative Bn. Yeah.
Yeah. Okay. And then when we combine those two inequalities together, we get that 2 epsilon is bigger or equal to Cn minus Bn.
So that's 2 epsilon, right?
Yeah, 2 epsilon. So we just add both sides together.
Okay.
But this guy is exactly the absolute value of Cn minus Bn. All right.
Okay.
But this is a contradiction.
Yeah.
Because Cn minus Bn is supposed to go to 0.
Yeah.
So this contradict. The fact that Cn. Well, I guess I would put the absolute value, but it doesn't change much. Cn minus Bn is supposed to go to 0, so I guess I can even get rid of those. Does Bn and Cn have same sign?
Have the same sign, right?
Yeah. So what we showed now is that we're able to make sense of what it means for a real number to be positive and what it means to be negative. And if this real number is not equivalent to the 0 sequence or 0, then there's only one case which is possible. I mean, you can either be positive or negative. You cannot be both.
Okay.
I mean, that's kind of the thing you expect, right?
Yeah. Yeah.
Like when you're both, you're supposed. I mean, it's just supposed to be you should be equal to 0. Okay. But now we can still. So now we can basically did what. So from that we can basically. So I will not do everything because we already did much of that.
Yeah.
But we can basically do the same thing we did with the rational. Okay. So we're gonna say that x and y inside of R. So if I take two real number x and y, I would say that x is less or equal to y if y minus x is positive.
Okay.
I guess I will put strict inequality for now. Okay.
Okay.
So it's basically the same definition we had before, and I mean we just basically define what it means to be positive from the previous lemma. What it means to be negative, and also I mean we will do the usual stuff, and also x is less or equal to y if either x is strictly less than y, or x is equal to y.
So it bases. So what you wrote is, and also x is equal to y, or x is
it's less or equal to y.
Less
if
than or equal. Okay.
If either you have x is strictly less than y, or x is equal to y.
Okay.
Okay. And I will also leave that as an exercise, but exercise. This is a total order. Of the real numbers. Okay, so this should probably ring you a bell. It's pretty much the same thing we did with the rational.
So we have to prove that it's a total order of the real numbers, right? Okay.
Yeah. So you can compare every real number between each others, and there will always have one which is bigger or equal to the other. Okay. Okay, now we can basically do I mean, here we're gonna have a lot of repetition, but I will just state it fast. So we can define the absolute value of a real number. It will be the maximum among x and minus x. Okay?
Okay.
So now that we have a sense of ordering, now we can make sense of what it means for x or minus or x to be maximum, and this allows us to copy the definition we had before for the absolute value. Therefore, we have this. Okay. Is that good for you, Peter?
Yeah, because I'm starting to remember the other definition of the absolute value. Like, if you don't mind me writing it.
Yeah, you can write.
That's way too thick. Because I remember I saw this in like a book where it's like if x is greater than 0, then
you just rose x.
Like now I'm trying to remember it. Because like it's x if x is greater than 0, it's negative x if x is less than 0.
Yeah, and you probably want to have an equal sign.
I thought I would write that.
Yeah, those are definitions are exactly the same.
Yeah, that's what I remember from the absolute value definition.
Yeah, the only thing is that you need a total order to be able to make sense of those, but once you have that, then you can define the absolute value as we did. So yeah.
Oh, okay.
Okay, what next? So as we have now absolute value, we can define distance. We have a distance function. it takes two real number and give you a real number, so a positive number, I should say. And what it does, it just takes x and y and just evaluate the absolute value of x minus y. So this is the same definition we had. Maybe I should put something like that for the Q, right? For the rational.
Yeah.
And this turn R into a metric space. Okay.
Mm-hmm.
And I mean, the notion of metric space. So what the reason why I introduced the notion of metric space will now finally pay off. Mm-hmm. So all the definition of convergence and being Cauchy, I all introduced them for a metric space, right?
Right.
Therefore, as now we have a distance function over the real number, now we can make sense of a convergent sequence of real number and Cauchy sequence of real number.
Mm-hmm.
Therefore, all the theory of convergent sequence / Cauchy sequence applied to this case. So I think we had a number of lemma that we had. So for example, one thing we showed is that a convergence of a sequence is unique. So if you have a sequence that's converged, then the limit must be unique. But as we prove that for the general case of metric space, then we automatically get that for free over the real number, because that's just a special case of this the thing we prove.
Okay.
So that's kind of cool. And the definition of Cauchy sequence worked exactly. I mean, we can apply the definition we gave earlier, which were more general. Now they can be specialized to the case of a real number, and we get back the usual definition. Okay. Mm-hmm. And maybe I will just recall something that I mentioned once. Maybe you don't remember, but we said that a metric space, or maybe MD is a metric space. Metric space. Is called complete if all Cauchy sequence are converging. Okay.
Okay.
And one thing that we saw with the rational, I mean, that's kind of the whole point of constructing the real number, was that the rational were not complete.
Yeah.
And now one of the new goals that we have is to show that R with this absolute value that we defined earlier, I mean, I should say the distance that we defined earlier, is a complete metric space. Okay.
Okay.
Because what we did is we basically did some guess, right?
Uh-huh.
We look at Cauchy sequence, and we saw that Cauchy sequence are kind of interesting because they're able to see points which are not there, right?
Yeah.
For example, they were able to in some sense to see the square root of 2, right?
Yeah.
But now the problem is, is the construction we gave using Cauchy sequence, is it enough? Mm-hmm. Like, can we imagine like maybe they're able to find some points, but maybe they're missing some, right?
Yeah. There
could be like some kind of possibility. And one of the very important property of the real number is that's not the case. The real is indeed a complete metric space.
Mm-hmm.
So that's one goal. Maybe we're gonna leave for next time to show that all Cauchy sequence over the real numbers are converging.
Oh, okay. Yeah, I'm kind of interested in like how that's gonna turn out, because like if we think of like the whole set is containing a lot of Cauchy sequence. I'm like, how do you prove all the Cauchy sequence are conversion? It seems like it's an infinity amount of Cauchy sequence to deal with.
Yeah, we're gonna show that all of them are converging, so there's gonna be a big result.
Oh, that's gonna be exciting, because I'm like, how can you take something that's infinity and like prove that all of them are without going nuts?
Yeah, maybe I can. I will not prove that today. We will prove it a later day, but
yeah.
I want to show some cool property. Okay.
Okay.
So first of all, so every time we build a new number system, we already show we show that the previous system was inside of this one, right?
Yeah.
We started with the natural, and then we embed the natural inside the integer. We embed the integer over inside of the rational. Now we have to do the same with the rational inside of the the real number. Okay.
Mm-hmm.
So here's how I'm gonna define the map. Okay.
Okay.
So here's the inclusion. So we want to make sense of the statement that say that Q is contained inside of the real number, right?
Mm-hmm.
And the way we're gonna do it is we're gonna take maybe I will use the word Q because I think Q is kind of a good name for a fraction.
Yeah.
And what we're gonna do is we're gonna basically assign it the sequence an is equal to Q.
Okay.
And we're gonna put that inside of this equivalence class. And before we leave, I want to show that this map is injective. Okay.
Uh-huh.
Even we're gonna prove something stronger. Because this map is so Q has a notion of distance and R has a notion of distance.
Okay.
What we're gonna show is this map is injective, and furthermore, this map preserves the distance function. I mean, that's equivalent to say that the absolute value of a so that's equivalent to say that the absolute value that we define over the rational would be the same for the inside of the real number if we consider this inclusion map.
Okay.
Okay.
Uh-huh.
So the proof is gonna be very not interesting, but it's gonna be an important step. Okay.
Okay.
So let Q. So let Q be a rational number. Okay.
Mm-hmm.
I guess we can assume. Okay. I guess we have two cases. Either Q is non-negative or Q is negative. Okay.
Mm-hmm.
So first case, maybe it's not. I don't know. I'm not sure it was really necessary to split it in two cases, but let's do it like that. It's gonna be a little bit more clean. So in the first case, okay. So what our map is doing is we basically building the map n is equal to Q, right? The constant sequence, right?
Uh-huh.
Well, actually, I need three cases. Sorry. We're gonna split into three cases. We're gonna have the case where Q is equal to 0, but the case with Q is equal to 0 is not very interesting. So maybe I'm gonna call this the first case and second case because the two are similar. I'm gonna do both at the same time. So if an is equal to Q, right?
Yeah.
Then those definition that Q is positive and Q is negative, this is inside of Q, right?
Uh-huh.
This is using the definition of what it means to be positive and negative inside of the rational. So now we want to think about what is the sign of this sequence as a real number. Okay, maybe I will just do first case, but in second case I will just say it's the same. Okay. So if we're in the first case where n is equal to q, so as q is positive, then from the definition of positivity, we have that an is positive, right? Because all the terms are positive, and that's exactly what it means for. Well, actually, the condition is kind of weaker because over the real number, real numbers are equivalence class of Cauchy sequence, and we said that a real number is positive if we're able to find some sequence inside of that class which is positive, right?
All right.
But here we don't have really to find a sequence which is positive because we already have an obvious one that we can choose.
Okay.
Therefore, n is positive. Well, I guess the proposition I wrote is not really well written. Well, I guess the proposition is not going to be very interesting. So the absolute value of an, right? Yeah, I guess maybe I will. Okay, I will forget the part it preserved distance. Okay. I will just show it's injective. Okay.
Okay.
Not bad. Because here the definition is a little bit subtle because we define. I mean, okay, here I'm kind of cheating when I said that R is having a metric space structure because when I define metric space, well, I don't know if you remember, but I said that the distance function takes value inside of Q, right?
Yeah.
But then I said it was not really an issue because we could replace Q by the real number and we will still get the same definition. But if I want to compare the two notion of distance, so the one we had before was defined over Q, right?
Yeah.
And now the new distance function that I gave you is defined over R. So to be able to compare the two distance, I already need a definition that Q is contained inside of R. I already need this fact, so I cannot really show the last part because the two things are not compatible right now.
Oh, okay.
So I will just show the map is injective.
Okay.
Which is not too bad. Okay. If and maybe let's give it a better name. Let's call it psi. I mean phi. Sorry. So if P and Q are a rational number, okay, and we have that Fp is equal to phi Q, okay.
Okay.
Then it means that the constant sequence an is equal to P and Bn is equal to Q. It means that an minus Bn is equal to 0, right? But if we will just write down what is this an and Bn, so an minus Bn, this is just P minus Q, right? Oh, sorry, I shouldn't write is equal to 0. I should say it's converged to 0. My bad. All right, like that. But then we get into trouble because the sequence is constant, right?
Yeah.
So if those guys are going to 0, it means that P has to be equal to Q.
Yeah.
That's the only way that that's the only way that P minus Q will go to 0 because otherwise this sequence is constant, but it's not 0. That cannot go to 0.
Yeah.
So P is equal to Q does psi is injective. Okay. I guess now it's going to be a bit of a mess, but I guess I will leave it as an exercise, but it's kind of a mess. So maybe I would put a rational number here. So we had a notion of a distance between the rational number, right? which was taking two rational numbers and was giving you some positive rational number, right?
Mm-hmm.
Now what we can do is we can compose it with our psi to get a real number.
Okay.
Okay.
Mm-hmm.
So I don't know how we should call this new function. So maybe we should call it. I guess we could put a little prime on. Well, it's not really a good idea. So maybe I would call the first one with the little prime and the other without the little prime, because we're gonna mostly from now we're gonna use mostly the second one. So using this composition, we get that the distance function is giving us a real number, right?
Mm-hmm.
And the exercise will be to show that distance over the rational of P and Q is the same thing as the distance inside of R of phi P and phi Q. Okay.
Okay.
Where this guy is the distance function for R. Okay.
Mm-hmm.
So this I will leave as an exercise.
Okay.
But this basically says that the whether you're measuring your rational number inside of the rational number, or instead of the real number with the embedding that I just described you, you will still get the same result. Both distance give you the same thing.
Okay.
And this will be important because what's going to happen is if the sequence is preserved, if I have a Cauchy sequence inside of the rational number, then it will automatically be a Cauchy sequence inside of the real number using these properties.
Okay.
Okay.
All right.
And yeah, it's pretty much what I wanted.
Okay.
Another thing I see we have to show, but this I will leave you. So I will leave you for next time. I will. Another thing which is important over the rational number is that, but this we'll have to talk about topology, is that this embedding of Q inside of R, that we just described it, is dense.
Okay.
Okay. And one way you can think about density is to think that every real number can be approximated by a sequence of rational number.
Okay.
But that's something we're gonna need to make sense when we talk a bit about topology next time.
So basically, what you said is every real number can be written as a sequence of rational numbers. Is that what you said?
Yeah. So you can always find a sequence of rational which is converging to a real number. So if you start with your favorite real number, I will always be able to find you a sequence of rational that's converged to this number.
Oh, okay.
For example, you give me pi, but then I'm able to
right,
find
as
you
a sequence of like rational numbers that can give you pi.
Yeah.
Okay.
You basically saw an example last time with square root of 2.
Yeah.
So we wrote a sequence of rational number which converged to square root of 2. Well, basically we're going to show it's always possible to do that for every real number.
So basically when you say dense, it just means like every single number, like every single real number can be represented by a sequence of rational numbers, right? So
yeah.
I guess the mathematical definition of density in this case is sort of like if you're given a set and it's a subset of another set, you can basically say that does it have to involve just sequences, or can it be involved with functions and stuff?
So it's going to be about, so usually density is it's kind of a general thing.
Yeah.
That you can make sense in topology, but if you are in the context of metric space, density is equivalent to check that every number can be approximated by another family of by a subset of it.
Oh, okay.
So here, for example, every real number can be approximated by some rational. Right?
Yeah.
But okay, maybe I can give you a better example of a density theorem that sometimes people use in analysis. For example, if you're working over So you mentioned functions. There's actually density theorem for functions which are very useful. For example, so okay, we need a notion of distance for function, which is not very trivial, but let's imagine you have one. Okay.
Yeah.
And I mean, I will not describe it. It's called. I mean, if you want to be very precise, you have to choose the uniform norm, which give you the uniform metric. So. But this is a bit. So it's just some kind of way to measure like distance.
So density varies within what you're talking about mainly.
Yeah, it depends on the topology you use, and that's pretty much it.
So what we need to know about it right now is just basically every, if you're given a set, you basically are able to explain that set through a sequence of the subset within that set.
Yeah. So basically, you can study the real number through the rational, because basically every real number can be approximate over the rational. So, so basically, if you have some property that hold for the rational, you can pretty much extend it for free over the real number, because you can use the density argument. Okay. And so there's also example with function. For example, in certain sense that I don't want to describe in detail, because otherwise it's going to be too complicated. Yeah. But in some sense, every continuous function can be approximated by a polynomial function. Okay. And sometimes in analysis, you will see people proving stuff about polynomial, and then they will try to use this density result to prove the general case for a general continuous function. This is called Weierstrass approximation theorem.
Oh, okay.
An important theorem in more complicated analysis.
Oh, okay. So what are we going to go over next time?
So it kind of depends on your vibe.
Okay.
So how do you feel with the exercise right now? Are you like have you done some of them?
No, I have to actually like do some of them. Like I'm still like on the one that we started out in the first week, so I have to actually like go over some of them and look over the video notes for those.
So maybe what I suggest is maybe for the last two days of this week, maybe you should go over them. What do you think about it? So I'm a bit also busy this week, so and I think we shouldn't go like too far without you like having done the exercise, because otherwise it's kind of hard to assimilate the knowledge, right?
Okay.
So maybe but I don't know, what do you think about it?
I think it's like whenever you explain it, it's like I follow through, but then like when it comes to actually doing the exercises, I think it's like I have to think about the definition, and then I have to think about the technique. So yeah, I probably have to work on that. I think for me, it's like when you explain it, it feels as if I can solidify exactly what you're talking about, like when it comes to the definitions and stuff. But I think when it actually applying it to the problems, I think that's when I actually have to like think about them more deeply. Yeah. So what I advise you is like, I mean, you're not forced to do like all the exercise in order, right? Yeah. So maybe like instead of starting with the first exercise, you can choose like whatever you prefer in the first two sheets of exercise. You can think about the one you think it's cooler, or the yeah. And I think I have to go back to a couple of our past lectures to get the other exercises.
Yeah. For example, I thought you were like kind of enthusiastic about proving the reverse triangle inequality. Well, this is one of the exercises of sheet 2. So maybe if you think it's cool or interesting, you may want to start with it. I don't know. Yeah. It's more up to you, but yeah. Yeah, and if it's really too hard, you can also like check the solution, but at least try to work a solution on your own. Okay.
Yeah. I try. I try not to look at the answers as much, but the thing of it is that for me, it's like sometimes I wait too long, and I practically like don't look at the solution for days, and then I realize like, oh, I haven't tried the problem yet, and then I realize I'm still stuck.
Yeah, you can look at solution after a while, but like I mean, at least like try a little bit, okay? Because I mean, basically, the only thing you have to be careful is just not to look at the solution right away, because otherwise you're gonna read the solutions, get, oh yeah, everything makes sense, but I don't really. I mean, when you read it, but when you're trying to do a similar problem, you didn't really learn about it, and
I think for me it's like I'm trying not to make it seem like, oh, like I don't get it within 20 minutes after thinking, and then like after like say like I wait 20 minutes or like a half an hour and I'm still stuck, I look at the solution, but then I'm like, oh, I'm gonna copy the way they did the solution with like other questions that are similar, and then I just keep doing that. But at the same time, it feels as if I didn't fully solidify the logic or solidify the method in my head, or like the way I should interpret the way to think about the problem. So like that's the one thing with me is like if it's like in a textbook, like basically I will just kind of like memorize how to solve it in a way, and I'm trying not to do that as much with math proofs, but it gets even harder at that point.
Yeah. But you usually it helps a little bit to struggle on the proof first, and if you're stuck, then look at the solution. And if you struggle a little bit before, then you're gonna be very attentive about the proof.
Yeah, like for me, it's like when it comes to like say simple proofs, like like say like if you add two even numbers together and then it turns out to be like this number, right? Those I can figure out easily because I know what the definition of a even number is and a definition of an odd number. And I can just basically write the proof, like making it look like it's like algebra in a way, like just basically just writing it out, like basically how to like, like equate it. But then like when it comes to say like divisors and all that stuff, then I have to think about more deeply. I guess like for me, it's like, default. It's like when you've done a problem so many times, you realize that, oh, I just have to write it like this. But I know that some proofs it's not like that. You just actually have to like look at the problem and basically are like, okay, what do I have to think deeply about, like say a function, or what do I have to think deeply about this definition or that definition, and what can I do to show this or something like that. Does that make sense?
Oh, sorry, I was mute. I was saying it's fine.
Okay.
Sorry, I was like kind of talking. I was like, oh, I don't get any answers.
Okay, so I think we went over like everything so far. So anything you would like to say to our global audience, Sascha, before we depart for today?
So drop the follow, drop the bell, drop the subscribe, drop the same thing inside of YouTube, and I guess go on Discord.
Yeah. And also, sorry I didn't say hi to you in the beginning, Don. So if you guys are not familiar with Don Factorial, I know you changed your name, so Don Factorial, he also does like math streams, and he's also doing general relativity, so I'm actually like pretty stoked that he's actually doing that. So he's another math streamer, and I guess like / physics streamer now, since he's doing general relativity. So yeah, like, and also I've been reading that that mathematical physics book that you recommended, Sascha. I thought it was pretty interesting. Like I read up to like page 7, and it was funny that they were introducing like basically like 4-dimensional space. It's sort of like they said I think they said like events is sort of like a linear mapping, and I was like, oh, that's from linear algebra.
So you mean the proof by Vladimir Arnold that I sent you?
Yeah, I think it was
Principle of Classical Math.
By Vladimir Arnold. Yeah. That book. Yeah, I was reading up to page 8, and I was like, oh, this is interesting. So they're bringing like linear mapping about events and all, like events in space-time, and I was like, oh, that's really interesting.
Yeah, I mean the first chapter are quite reasonable. Like what is chapter? Chapter 1 is Newtonian mechanics. Second one is Lagrangian. Third one is Hamiltonian.
Yeah. So I was like, oh, now this is what I was kind of looking for, because it was like, how can I bring like mathematical proof methods into like a physical domain? And I think that was the thing that I was trying to look for.
Yeah.
Because like the thing of it is that like, I can learn like physics, and I am doing that now. Like I actually did like a physics problem this morning. Not a complicated one. It was basically just revolved around a canoe and tension from the dock. So like, it's one of those basic ones. but like for me it was like, how can I combine my knowledge of like, I guess like mathematical definitions into like a physical sense within like physics? And I think that's like the hard thing to do. And like I think like with the book you recommended, I was like, oh, okay, now we're actually getting into like more like bringing into like mathematical abstraction into the physical, like I guess the physical construction of a physics problem, or at least like a physical mindset in that way. And I think that was the thing I was looking for, is like more like a mathematical physics definition of how to actually approach physics problems in that way.
Yeah, I mean, this is a great book. Yeah, I mean, the end is a little bit more advanced, but I think if you go to the first three the chapter on up to Hamiltonian mechanics is going to be pretty good.
Yeah, I think like for me, it's like when it comes to mathematical proof problems, I know it's like cool, and I know that it revolves around just purely math, but when it involves like math and like things like space-time and stuff, I get more interested in it because it makes me feel like I'm actually manipulating like I guess like the reality space that I have in my imagination in that way, because it's like more connected. Because I think I sort of like how Richard Feynman viewed mathematics. Like he wanted to do it, but then he ended up doing physics because like math was a little bit more abstract for him. Like I love the abstraction, but at the same time it's like, how can I make it more visual in my head? And the only way I can do that is through physics.
Yeah, I mean, Raziel is kind of like he was a really great guy.
yeah, he knew how to teach himself, and like, you know, I think that's basically the point of our streams, is just like, even though like I'm following along with what Sasha's saying, that doesn't mean I like understand like 100% of what he's talking about, but at the same time I try to restate it in my own words. That's why you guys like hear me restating a lot of what he says, because it allows me to like relay it back in my head. And it's like, actually, like when we were talking about, say, like what the real numbers are, which is the Cauchy sequence over the ideal, I had to restate it in my own words, and hopefully it helps you guys out whenever I restate things, because, you know, probably you guys are already in university and you're actually studying this stuff, but you want to do it in a different way than, say, like what your professor has like lined up for you. Because like this is the reason why I like Sascha basically talking about rings and talking about fields, because he's actually bringing the cool stuff in math that we don't learn until like probably like another class later. So it allows us to get in tune with the mathematical world in a more diverse way.
Yeah, I mean, so especially when you're undergrad, I mean, you feel like there's like an algebra and then you have analysis from both corners.
Yeah, the thing is,
but in reality, both are really like related to each other. I mean, at least in my field, like the two are like very like intertwined together. So
yeah, I am kind of like impatient sometimes, because the thing of it is that like I'm the type of person that would be like, okay, do I need this prerequisite? If I don't need it, then I don't study it. And like, you know, it's like I end up wondering, it's like, do I really need this? Because like the stuff that I want to learn, like right now I'm like between Calc 2 and Calc 3, but I don't remember that much from Calc 2. But at the same time, I try to pick it up a little bit. I don't know that much about Calc 3 except like, you know, gradients, divergence, you know, like all the vector calculus stuff. I don't know that much about Stokes' theorem. I don't know like surface integrals. I know I need those. I also know like with linear algebra, I need to refresh some stuff about that, especially with linear transforms. But at the same time, I know the point where I want to get to is way farther ahead, and I know I'm not ready for those. But at the same time, I'm the type of person that would just pick up a book on those subjects anyway and just read it, even though I will get totally lost.
Yeah.
It's like, for me, it's like I just don't want to go through like a whole semester of just like studying like one class material, but at the same time, I have to constantly do research to basically say, okay, what do I need? What is important? And then how do I go about it? And I don't have a clear map of that. But sometimes I get too impatient and I just study something that's totally over my head. And
I mean, that's fine. I mean, if you're able like to find like some goal or motivation to do something, I guess it's pretty.
That's why my study method is like so haphazard, because it's like like I'm probably like reading about general relativity when I don't know that much about tensors, and then I'm reading about tensors before I know about covariant and quadravariant components. It's like it's like basically I'm trying to expose myself to these things, but at the same time it's like I'm like trying to put the puzzle pieces together when the puzzle pieces are from totally different boxes.
Yeah. I mean, when I was in undergrad, I was a lot like that. Nowadays, I'm a bit like I don't know. I'm getting old mathematically, so sometimes I'm like, well, I'm not very excited about those new ideas because I mean, what are they gonna do for the problem that I cares?
Yeah, that's why I feel like very guilty when it comes to physics because I want to do like the more advanced stuff that involves like partial differential equations, but I'm nowhere near that. Like I want to just pick up like classic mechanics and just do like things like with the Lagrangian and stuff. But at the same time, I know I haven't done that much when it comes to just regular Newtonian mechanics and just doing the algebra of solving like say a thermodynamics problem or something like that. And like for me, it's like, oh, I don't want to pick up this university physics textbook and just do like a bajillion problems just from this like beginner stuff, like, you know, because I want to go deeper into the math and stuff, you know.
Yeah.
But that's just basically the immaturity of like how excited I am to get to this part. But at the same time, it's like, am I that dedicated to learn all the stuff from the textbook, you know, from like the beginners part of the textbook?
Yeah. I mean, yeah. I mean, I don't really. I mean, I really like read the entire textbook.
Yeah.
Like from the first like time.
Yeah.
Like for example, I started in differential geometry, and we have like Lie smooth manifold, but it's like 800 pages.
Yeah.
And I mean, there's like part I mean, when I started, I kind of read like some part like linearly, so I read like maybe chapter 1 to chapter 5 like kind of straight. And then I read like some chapter after that, and after that I was like completely like, okay, I mean, I don't see like the point of those concepts.
Yeah.
And basically I was not really able to like utilize them, and you know, I had no idea what they were useful.
Yeah.
And then when I get to when I meet like my supervisor for my master thesis, he was more like about giving you problem than doing like general theory.
Mm-hmm.
So he gave me like a problem, and was like, okay, I'm not completely clueless, but I'm missing a lot of tool, and I sort of learned like I sort of learned how you're supposed like to read those books. Like you basically like when you have a problem that you're interested to, you just have to like go to whatever chapter in the book like they're talking about the things that you care. I mean, maybe the thing is not very useful, but for example, in Lie you have a part on Lie group and Lie algebra. I'm like, what on earth are those?
Yeah.
And then I mean, after encountering them like in real problem, I finally realized why are they abundant and why I should care about them. And so yeah.
I guess it's similar to like say an undergrad that's doing like mathematics as an undergrad, and they're like, I want to do things like abstract algebra and number theory, but I have to get through like real analysis first, and they really hate real analysis. You know.
Yeah.
So it's like they don't want to go through like, I guess like the thing that they're not interested in just to get to the thing that they want to be interested in.
Yeah. So usually what I would recommend is to have like some minimal background. Like for example, you want to be very good at linear algebra because linear algebra is kind of every single field of mathematics uses linear algebra. So it's really hard to like do not know the basis of it. Yeah. But when you know the basis, you should like kind of jump to like small project. Yeah. Just with and like sort of learn like whatever you need on the pile, you know.
Yeah, I think it's because like people want to like get to the point where it's like, okay, I've got the basics down, that's it. Like I don't need to do any more because I'm not fully interested in this part. And I guess it's like they want to learn faster, but at the same time it's like they're given so much prerequisites. They're like they don't know which one to actually focus on. That's really important for the subject.
Yeah. Also, a thing I realized, which is a bit counterintuitive, but sometimes when you can spend a lot of time like doing a specific proof. Yeah. Sometimes it's like you understand less the theorem when you prove it rather than when you just play around with it.
Yeah, it's like when you're playing a video game and you play a boss that's extremely hard, and then you finally beat the boss, and you're like, wait, how did I defeat the boss again? Because you're just so into the game, you just wanted to beat the boss so bad, but then you just realized that you beat them, but you were like, how did I beat them technically?
Yeah, so it's kind of weird. I mean, there's a few there's a few theorems that I once proved. I mean, those are classical problems, nothing like crazy. Yeah. And like the proof was like super involving. It was like a lot of pages, but at the end of the day, I was not really understanding the theorem because I wasn't applying to like some concrete problems. So
yeah,
I don't know. There's like kind of a part that okay, maybe I will give you like a super complicated theorem, which is Atiyah index theorem, which is like a crazy hard theorem to prove. But I don't think like knowing the proof is that important. It's more important to know how to apply it to some problems to see how it works. Like proving the statement is probably not very useful because it will involve a lot of functional analysis, which are very complicated, and a lot of PDEs stuff.
Yeah.
But at the end, they don't really tell you how to apply it and why is this theorem useful in the first place.
Could you study functional analysis after real analysis?
Yeah, you could.
Oh, okay.
Actually, functional analysis is not that bad. I mean, you have to be comfortable with the like basic analysis because because it's going to be an extension of that.
Like, which would be like a better coherent path? Would it be like real analysis, complex analysis, and then functional analysis, or would it be like
for what? For learning functional analysis alone?
Yeah. So like, I mean, what would flow better? Like, would it be like you take real analysis and then you do complex analysis and then functional analysis, or would it be like a scenario where it's like you take real analysis but then you can take complex analysis and functional analysis at the same time?
I mean, complex analysis is completely a course on its own. Like, it's not like that even related to like real analysis. So you can probably like, I mean, for functional analysis, you probably want a course in, maybe the first 2 courses in real analysis. And after that, I mean, maybe you want to pick up topology, but you don't need that much. You just need to know about the metric space stuff. And then you can start functional analysis.
Like I asked because like...
you also need linear algebra, I'm sorry. Yeah, linear algebra is an important part of the functional analysis.
That's what I'm asking. It's like, like what subjects of math that like, even though it won't add to it, but you could probably make it more fun if you basically have more math under your belt. That's why I asked.
Yeah, but again, it kind of depends why you want to do functional analysis.
I saw like there was this book on functional analysis. It was for like engineers and physicists, and I thought that like it would probably be a little bit interesting to read that. I think it's by no, I don't think it's Sakurai. I think it's another mathematician. I don't remember which his name is. I know he's Japanese.
So those are probably, I mean, if I have to guess, this book is probably more about PDs.
Yeah. That's what I was
maybe
guessing.
Like stuff like reproducing kernels, stuff like that.
Yeah,
which are very like the most applied stuff in that.
Yeah, and it's also funny because I think like in the
but if you want
in the mathematical physics book you recommended to me, they said something about kernels representing like I think like representing like the space in which like 2 events that could probably, if it has a distance of 0, then basically they happen simultaneously, which I thought was pretty interesting in the use of linear algebra, because I was like, oh, I know what a kernel is. I recognize that.
So if you want a good project in functional analysis, which is fun, I mean, first of all, this is not even considered sometimes functional analysis, you just consider like model analysis.
Yeah.
One theorem which is very cool, which is very useful, is the existence and uniqueness solution to system of ODEs.
Okay.
The proof is not too involving.
Yeah.
I mean, okay. Existence and uniqueness is not too bad. Smoothly dependent, that's kind of an annoying proof.
Yeah.
But yeah, that's kind of a reasonable first like goal to have in functional analysis. After that, one which is very popular, especially if you're like kind of interested to like stuff that are related to physics, is trying to prove. I was about to say Lefschetz principle, but that's not it. That's kind of the most famous PD problem of all time. What is it? Well, I'm having a blank. Principle. Well, and basically, it's about the solution to Poisson equation.
Oh, okay.
Wait, what am? Dirichlet principle. Oh, there you go. Yeah, Dirichlet's principle is one of those very, very, very classical results in functional analysis and PDEs.
Okay.
It was kind of Hilbert, like in the beginning of the 20th century. That was one of his big problems he wanted to solve.
Mm-hmm.
It's formalize the Dirichlet principle, so he had to invent basically functional analysis and topology to do that. But this theorem is like very important.
I see. Okay, guys, so I think we're gonna end the stream for now. If you're watching this on YouTube, you know, like Sascha said, drop a like, comment, and subscribe to the YouTube channel if you're watching this. I will also post the Discord as well as the YouTube channel and Twitch. So if you guys wanna sub through there, you can do that as well. Join us on the MathSpellBook library Discord. You can also join my Uncle Talks channel, which is basically my video game channel where I just basically play video games and talk to you guys like about anything besides math. But you can also talk about math there. So like Sascha suggested, I think tomorrow we're not going to do a lecture. We're probably going to actually do problems, especially the problems that he assigned. So I think that would probably be a better use of stream time so that we can catch up on what the next part of what he will explain to us involving metric spaces as well as the real numbers. And I think that would be and I think for the rest of the week we'll probably just do problem solving. So I think that will probably get us up to speed to actually do those problems. Alright, thank you Sascha again for like another awesome lecture. I really appreciate it. You always coming through.
See ya.
Alright, take care, man. Alright guys, thank you for joining us today. I know we ranted a little bit at the end, but hopefully you got something out of it. But always remember guys, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care guys, bye-byes.